Hello everyone. In this video, we are going to learn about multimodal deep learning diagnosis of Parkinson's disease. Introduction to Parkinson's disease. Here we are going to cover like what is Parkinson's disease, symptoms and impacts, and the prevalence and demographics. Like first one is what is Parkinson's disease? Parkinson's disease is a chronic and progressive neurological disorder that primarily affects the motor system. It is characterized by the loss of dopamine producing neurons in the substantia nigra region of the brain, leading to tremors, stiffness, and impaired movement. Now we will see what are its symptoms and what is its impact. The main symptoms of Parkinson's disease includes tremors, rigidity, slowness of movement, and postural instability. These motor impairments can significantly impact a patient's daily activities and quality of life, often leading to difficulties with tasks such as walking, writing, and speaking. Now we will see prevalences and demographics. In Parkinson's disease, which is the second most common neurodegenerative disorder after Alzheimer's disease, affecting approximately 6.1 million people worldwide. The disease typically affects individuals over the age of 60 through early onset Parkinson's can occur in some cases. Current diagnostic challenges include subjective clinical assessment, lack of objective biomarkers, complexity of disease progression, and subjective clinical assessments. Currently, the diagnosis of Parkinson's disease relies heavily on subjective clinical assessments by neurologists who evaluate the patient's motor symptoms and medical history. This approach can lead to delayed or inaccurate diagnosis, particularly in the early stages of the disease. Coming to the lack of objective biomarkers, unlike many other medical conditions, Parkinson's disease lacks a well defined objective biomarker that can be used for diagnosis. This makes it challenging to differentiate Parkinson's from other similar neurodegenerative disorders, leading to potential misdiagnosis. Complexity of diagnosis, complexity of disease progression. Here, in Parkinson's disease, which is a complex disorder with a highly variable presentation and progression, making it difficult to accurately predict the course of the disease and tailor treatment plans for individual patients. Motivation for multimodal approaches, which includes limitation of unimodal approaches, leveraging complementary data, and then improving diagnostic accuracy. In limitations of unimodal approach, here we rely on a single data modality such as clinical assessments or neuroimaging alone, which can lead to incomplete and inaccurate diagnosis of Parkinson's disease. A multimodal approach integrating diverse data sources is necessary to capture the full com- complexity of the disease. In leveraging complementary data, here we are combining various data modalities, including clinical, neuroimaging, genetic, and behavioral information. The multimodal approach can provide a more comprehensive and accurate representation of the underlying pathophysiology of Parkinson's disease. Improving diagnostic accuracy. Here we are integrating with multiple data sources through advanced deep learning techniques, which can enhance the ability to detect Parkinson's disease in the early stages, leading to timelier interventions and better patient outcomes. On this slide, we are going to see about the model architecture and data inputs, which mainly includes data inputs, model architecture, and then the feature extraction and the fusion. In data inputs, here the multimodal deep learning model, which leverages a diverse set of data inputs, including clinical assessments, neuroimaging scans like MRI, PET, DAT scan, genetic profiles and behavioral data. And then coming to the model architecture, here the model employs a modular multi-branch deep neural network architecture that allows for the simultaneous processing and integration of various data modalities. This enables the model to capture the complex interactions and patterns within the data that are indicative of Parkinson's disease. In feature extraction and fusion, we mainly come across the model utilizes advanced feature extraction techniques such as convolutional neural networks for image imaging data and recurrent neural network for time series behavioral data to generate robust representations. These features are then fused together to provide a comprehensive diagnostic assessment. Training and validation strategies, which includes data curation, cross validation, and then iterative refinement. In data curation, here the researchers carefully curated and reprocessed a large diverse data set of Parkinson's disease patients and healthy controls, ensuring high quality and well annotated data for model training and validation. In cross validation, the model was trained and validated using robust cross validation techniques such as K-fold cross validation to ensure the generalizability of the model's performance and to mitigate overfitting. In iterative refinement, the model architecture and training strategies were iteratively refined based on the result of the validation process, allowing the researchers to optimize the model's diagnostic accuracy and reliability. Clinical implications and future directions, which includes early detection, personalized medicine, accelerated research, and then the future developments. In early detection, the multimodal deep learning approach can enable early and more accurate diagnosis of Parkinson's disease, allowing for timely interventions and improved patient outcomes. In personalized medicine, by incorporating diverse data source, the multimodal can provide insights into the underlying pathophysiology of Parkinson's disease, paving the way for more personalized treatment strategies. In accelerated research, here the robust diagnostic capabilities of the multimodal can facilitate and accelerate clinical research efforts, enabling more efficient patient stratification and development of novel therapist interventions. In future developments, the researchers plan to further expand the model's capabilities by incorporating additional data modalities such as wearable sensor data and environmental factors to enhance the overall diagnostic performance. I hope the video was informative for you all. Thank you for watching.